So moving on from the elements, we want to move into how do we actually produce the compounds, the molecules that make up the body. We're going to start by defining the term ion and differentiating between anions and cations. We have the sodium symbol from the periodic table and the same atom of sodium that we saw earlier on. As we said earlier, there are 11 protons in the nucleus, 12 neutrons, and then 11 electrons around in the orbitals. Overall, this sodium is neutral. But if we focus on the electrons here, you might notice that we have 2 electrons in the first orbital, 8 electrons in the second orbital, and then in the outermost orbital we have only 1 electron. Even though overall we have 11 protons and 11 electrons, that 1 electron by itself in the outer orbital gives an instability to the sodium atom. Electrons don't like to be by themselves in these orbitals. The inner orbital has 2 electrons and is full. The second orbital has 8 electrons and is full. The third orbital can also hold up to 8 electrons, but it's not full, and that provides the instability to the atom. So how does it become stable? Let's look at a second element, chlorine. Chlorine has 17 protons in its nucleus and 18 neutrons. And because it has 17 protons in its nucleus, it has 17 electrons in orbitals surrounding the nucleus. If we look at that, we can see that the inner orbital has 2 electrons, the second orbital has 8, and so both of those are full. But the outer orbital has only 7 electrons. But in order to be full or stable, it needs to have 8 electrons. So it needs 1 more. And so how these atoms become stable is the 1 outer electron from the sodium will actually be given to the outer shell of the chlorine atom that only has 7 electrons, such that we end up with sodium ion that has all its shells full because it lost that 1 outer electron from the outer shell. However, because we now have 11 protons and only 10 electrons, the sodium ion has a positive charge. The chloride ion is the opposite. It has accepted that extra electron. It has a full outer shell with 8 electrons. However, it now has 17 positive protons in the nucleus and 18 negative electrons in the orbitals around it. And so the chloride ion has a negative charge. So an ion ultimately is an atom that has either gained or lost electrons and now has an overall charge associated with it because of the imbalance of the number of protons and electrons. The term anion and cation are just the specific types of ions that you might form. So in our example here, the sodium ion has a positive charge. And so yes, it's an ion. Specifically, it is a cation, because cation is a positively charged ion. The chloride ion is a negatively charged ion. The term for that is an anion. So overall, we have the term ion, an atom that has gained or lost electrons and become charged, but then an anion is a negatively charged ion, and a cation is a positively charged ion. So now that we've looked at the idea of what an ion is and differentiated between the anions and cations, let's identify the major cations and anions in the body. We've been talking about sodium already, and it is a major cation in the body. Other cations include potassium and calcium and hydrogen. Major anions in the body include chlorine, bicarbonate, and phosphate. But what are the major functions of sodium, potassium, and calcium? Sodium is a major extracellular cation found outside of cells. Its main functions are in water balance in the body, conduction of nerve impulses, and muscle contraction. Potassium is the major intracellular cation found inside cells. It functions in nerve impulses and muscle contractions as well, also cardiac functions. Calcium is another cation in the body, primarily stored in bones, and its functions are in muscle contraction, nerve impulse, and cardiac function, like potassium, but it also plays a role in blood clotting. Hydrogen will come up later in this unit in terms of discussing acids and bases within the body and pH. Now that we've identified the major functions of these ions, let's move on to differentiate between ionic and covalent bonds. These are two different types of bonds that act within compounds or molecules in order to hold atoms together. Let's start by looking again at the sodium and the chlorine atoms reaction, where the sodium atom gives off the electron, forming the sodium ion. The chlorine accepts that electron and becomes the chloride ion. In the end, as we've discussed, the sodium becomes positively charged and the chloride becomes negatively charged. So what ends up happening is that the positively charged sodium ion is attracted to the chloride ion that's negative, and vice versa. This is an example of an ionic bond, where we have gain and loss of electrons forming ions that are then attracted to each other because they now have opposite charges. We have sodium chloride as a compound. The other type of bond is a covalent bond. Here we have an oxygen atom. Oxygen is number 8 on the periodic table because it has 8 protons, as we discussed earlier. It also has 8 electrons in its orbitals. The first orbital is full with 2, but the second orbital only has 6 electrons. And so the oxygen atom, in order to be stable, would like to get 2 additional electrons in that outer orbital. If this oxygen atom was to come across some hydrogen atoms, the hydrogen atom has 1 proton in its nucleus and 1 electron in its outer orbital. It only has 1 electron, and it is in that first orbital that can only hold up to 2. The hydrogen atoms here are looking for 1 additional electron each in its outer orbital. In this case, each hydrogen wants an additional electron, and the oxygen atom wants 2 additional electrons. So we don't have a situation here where an atom wants to give up electrons, because in this case the oxygen atom would not want to give up 6 of its electrons, or even 1 to each of these hydrogen atoms, because it then still would not have a full outer shell. The hydrogen atoms, if they were to give up 1 of their electrons, then would not have a full outer shell either. So what happens in this type of bond is that the hydrogen atoms come close to the oxygen atom, and the oxygen atom will share 1 of its electrons, and the hydrogen atoms will share 1 of their electrons with the oxygen atom. So in the end, if we were to analyze using this picture each of the atoms within this water molecule, we would see that the oxygen actually has 8 electrons in its outer shell. If you look at the hydrogen atoms, they actually have 2 electrons in their outer shell. However, again, this is not due to a gain or a loss of electrons, but due to a sharing of electrons between the atoms. And this is what makes up a covalent bond. A covalent bond is a bond between 2 atoms because they are sharing electrons. In the end, you form a molecule. If we were to simplify this image by getting rid of all the proton and neutron markers, this is what we would have. The exact same reaction that we just saw a moment ago. As we said, we form a water molecule, and as it has listed here, we can also call it a compound. To move that off to the side, we can look at some other molecules here, because we want to ultimately differentiate between compounds and molecules. So here we have hydrogen. If we were to have 2 hydrogen atoms, each with 1 electron in their outer shell, neither would want to lose their electron, because then they would not have a full outer shell. And so a hydrogen molecule is formed when the 2 hydrogen atoms share their electrons, such that each ends up with 2 electrons in the outer shell due to sharing. And so this is a covalent bond that forms the hydrogen molecule. Another example would be oxygen, O2, where we have oxygen, each with 6 electrons in their outer shell, and they come together and actually share 2 electrons from each of them, so 4 electrons are being shared in this covalent bond that ultimately forms the oxygen molecule. We want to differentiate between compounds and molecules because here we have all these covalent molecules. All these molecules that are formed due to sharing of electrons. As you can see below, the water molecule is also listed as a compound, because compounds are just when 2 or more atoms come together in order to form a new chemical. But when we have covalent bonds forming, and we end up with a discrete compound like the water, that is 2 hydrogens for every 1 oxygen, or for the hydrogen molecule of 2 hydrogens, or oxygen of 2 oxygens. These are discrete molecules where, in theory, we could go zoom in on a water and find each individual molecule and pull them out. When we deal with ionic compounds, like the sodium chloride that we looked at earlier, we don't discuss them in terms of being molecules of sodium chloride. Sodium chloride is a compound, specifically an ionic compound, because if we were to zoom in on sodium chloride, we would see something like this, where we have this repeating structure to the salt crystal of the sodium chloride. Every sodium is surrounded on all sides by chloride ions, because the positive sodium is attracted to all the negative chlorides. And every chloride is surrounded by all sodium ions, because each of the chloride ions is an attraction for all the positively charged sodium ions. And you end up with this salt crystal. The idea here is you can't say which of those two are actually bound together. They're all attracted to each other, and you end up with this salt crystal for ionic compounds.